Good morning, good afternoon, good day. We're in lesson 12. This is video 12A. Very important chapter in this course. Normal models. Normal model is important for two reasons, and we'll see why in just a slide or two. So let's get to it. Normal model is a good probability model for quantitative variables. So we have to be quantitative, no categoricals here. Remember what we're doing is we're collecting data, so we'll have a list of numbers, and once we have a list of numbers, we'll graph it. If the graph looks a certain way, then what scientists, statisticians do is sometimes they'll try to model the data with a generalization of what's happening. So a normal model is a good probability model for quantitative variables. The histogram that you make needs to look like two things. One of them is unimodal. So we'll be looking just for one major peak or pileup of the data in the center, and symmetric. So your data needs to look unimodal and symmetric. If you can just think in your head, it will look like this. That's that familiar bell-shaped curve. A normally distributed variable has that familiar bell-shaped curve. And you can see it at the bottom of the page, so I won't draw it on here and then just erase it in 4 seconds. Okay, so the data is piling up in the center and then tapering off as you get to the extreme highs and the extreme low values. All right. Why is a normal model important? It's important for two reasons. The first reason is that in practice, many variables, when you collect data on a variable, they will look normal. Okay? The first reason many variables in practice are well modeled by a normal curve. And so here's some examples. This is not an exhaustive list, but if you look at heights of males just by themselves, the graph will look normal. The average height of a male is about 5'10", and so most guys are 5'10", 5'9", 5'11", a few inches off in either direction. But it'll taper off. If I get up to these high values, there are a few guys that are about 6'3", but not many. And there are a few guys that are about 5'3", but not many, right? So there's a few guys in the tails and lots of guys towards the center. If we looked at females separately, the average height would be shorter, but again, that bell-shaped curve would describe the distribution of female heights. Weights and other measurements of things that are manufactured are typically normal. So for example, if you were packing up bags of potato chips, you would get a normal model if you looked at the weights. IQ scores is a very famous example, newborn birth weights, and a plethora of other natural phenomena. So the first reason is that many things will look normal. Okay? We'll collect some data on a variable that we're analyzing in this course. The graph that we'll check first to see if a normal model is appropriate is a histogram. And that's, of course, the first graph that we'll always start with when we're graphing a quantitative variable. Okay, there is a second graph to check, and there's a reason we'll need to check both. What it's called is a QQ plot. We'll do that towards the end of lesson 12. The QQ stands for quantile-quantile. It's sort of a technical graph. The reasons why it works is not quite that important for this course. But we'll have to check both because sometimes things are hidden in a histogram that might trick us into thinking something's normal, and when we check that second graph, the QQ plot, then it'll be revealed that possibly a normal model isn't appropriate. Okay, so what happens is we'll have data, we'll look at the two plots and sort of make an assessment, is a normal model appropriate for this variable. Big key here, do not assume that a variable is normal without checking the graphs first. Remember, the first step always when you have data is to graph it. Example time. Down at the bottom of the page, a Baltimore doctor graphed the heights of all of his female patients, 277 patients. Comment on the graph. There's two parts to it. It's very faint in your notes. It's probably faint on this video, so let me just do this. And maybe in your notes, do the same thing. I want to put some comments on what this graph is. So number one, there's two parts. All the rectangles, the blue rectangles here, this is the data. right? This is graphed with a histogram. When the doctor graphed the patient's heights, right, here's 65 up to 66, and how many females were in this 1-inch bin here, right? So I would go up to the top and I can see that there were over 50 females between 5'5" and 5'6". And so the blue histogram is a graph of the data. In this chapter, we notice that this graph has sort of a pattern. Now, it's not perfectly normal. You can see that for whatever reason, there are sort of a couple of extra ladies here. The normal model is the smooth curve. If you look at this smooth bell-shaped curve, this is the normal model. Okay, the normal model looks to be centered somewhere between 64 and 65 inches. And remember what a model is. It's a generalization of the data. For the most part, the model does a pretty good job of describing what's happening, but it's not perfect, right? There's some sort of space up here where the model's not perfect. We have a few extra ladies poking out here outside of the model. We've got this one thing. But if you had to pick one model that seems to do a pretty good job of describing the trend or the pattern or the relationship here, this normal model seems to do a pretty good job, right? Normal models, you can see a few things here. Most of the data is piling up in the center. So the average height of a female in America maybe is about 5'4", 5'3.5", 5'4.5", somewhere in there. And most of the female patients from this doctor are here. And we can see that because the rectangles are taller. As you have taller heights, there are fewer females up here. As you have shorter heights, there are fewer females down in the left tail, right? And so the data is tapering off. In both tails. All right. So whereas in this graph here, this data, a normal model is not perfect, but it seems to do a pretty good job. That data, the blue rectangles, the words we would describe it, looks pretty unimodal and looks pretty symmetric, right? So normal model, there it is. We'll flip over to the next page. First reason why normal models are important, lots of things are normally distributed. Second reason, all the theoretical stuff that's sort of the basis for the second half of this course. All right, so here's the trickier reason. But a second reason normal models are so important is that theoretically, many statistics, like the sample proportion, comes in less than 14, and statistics like the sample mean, which will be less than 18, follow a normal model under certain conditions. And this might not seem amazing at this point, but because of this amazing fact, we can build the foundations of all the things we're going to do in Unit 3, which is lessons 14 to the end of the course. So we'll sort of save this idea for later. I don't want to get into it because I'll talk about it for an hour, and we want to keep these videos manageable. A normal model is a probability model. In the previous lesson, we talked about probability. A normal model is a probability model. And so we need to use this idea we touched at in the previous lesson. We can find associated probabilities by looking at the areas under that normal curve. So to show that, let's go back to the doctor's example with the heights of females. The doctor from the previous page used the appropriate normal model to answer the following questions. What we have here towards the bottom of the page in your notes, there's two of them. This is output from StepCrunch. Okay, we will need to use StepCrunch to answer normal model questions. Okay, so part A, just get the flavor of sort of how this works. What percentage of the female patients in Baltimore are 5'8" or taller? All right, so remember this model. This model here is based on the doctor's patients. This is based on I hope it was 277 patients. Trying to remember off the top of my head. So this model, I'm going to generalize to Baltimore, but this model is not perfect, so we're just getting a ballpark estimate. What percentage of female patients are 5'8" or taller? 5'8" is how many inches? 68 inches, so we'll probably have to convert that. The smooth curve. So from the data, the doctor's patients, the average height was 64.42 inches. You can see that in your notes. And the standard deviation here was about 2.26 inches. So this normal curve is based on these two parameters, and we'll talk more about that in the next video. But there's that smooth curve. To answer the question, it's pretty easy. I want 5'8" or taller is 68 inches. All I do is go under my normal model here from 68, and because we want or taller, we go up. And that shaded area is the answer to the question. So we'll do this often, but areas under the curve correspond to probabilities or proportions of the whole population. So what percentage of the female patients are 5'8" or taller? You can see down here, the StatCrunch tool will give us the answer. There's really no other way to get the answer. That area is 0.05, oh, we can round it to like a 0.57. The whole area is equal to 1, or 100%. So this little part here up in the upper tail is only about 5.7%. Right, move the decimal and put the percentage sign. So what percentage of female patients are about 5'8" or taller? Based on the model, our best guess would be about 5.7%. All right, so that's the first part. And we can go backwards down in part B. Part B, let's clean this up here. What's the 25th percentile for female height? All right, again, normal model questions will have to resort to the StatCrunch tool. You can see the, well, you can see the answer at the bottom. The StatCrunch tool gave us the answer. I'm just going to talk about it. All right, so here's what we did this time. 25th percentile says, I need to solve for the height. I don't know, I'll call it X here. What height? This is my number line with heights on it, horizontally. That's the answer to the question. And what we did is we put 25% of the shaded area, the total area, to the left, and that would leave the rest, which is 75%, or 0.75 up to the right. Now, if I shaded right at the center here, at the 6442, it would be 50-50. Okay, so we need to be to the left of center. 25th percentile, 25% to the left. And if you're this tall, what that means is you're taller than 25% of the population, and 75% is taller than you. To get the answer, we have to use the StatCrunch tool. It's down here. And the answer is not 0.25. The answer is the 62.89, blah, blah, blah. All right, so what's the 25th percentile for height? About 62 point, oh, we can round that to, say, 0.9 inches. It's a little bit under 5'3". Okay, so if you're a female in the Baltimore area, based on this model, we're calling 62.9 the 25th percentile. All right, we'll use this tool often. It's sort of the only way to get the answer for these questions at this point. All right, a couple of definitions on the last page, and then we'll end this video here. How do we specify a normal model? There are an infinite number of possible normal models, and they're based on two things, two parameters. Okay? And parameters are numbers that describe a model or a population. One thing we need to know is the mean. So where's the center of that normal model? The other thing we need to know is the standard deviation. If we know the mean and the standard deviation, in other words, the center and the spread of a normal model, we can totally describe the normal model, and then we can calculate probabilities and percentiles as much as we want. Now, There are different symbols. If we're working with a model, we have to call the mean mu, and it would look like that. It's the Greek letter M. Okay, so this is mu. I'm not sure if this has come up in this course yet or not. Possibly it has. But there's mu, and the standard deviation symbol is sigma. If we're talking about models with model parameters, these are the symbols that we have to use. Okay? They are different than what's going to come on the next slide here. Parameters are numbers that we choose to specify a model. We don't want to confuse those with statistics. When we collect data, you have a list of numbers. We've collected a variable in class, for example, heights of students in class. We can summarize it by calculating summary statistics. Remember, after collecting data, we can calculate the mean, and we would call it y bar. Different symbol for the sample mean or the mean of data. Okay? We can also calculate the standard deviation from data, and we would call it S. So you have to understand, are we talking about a model, then we'll be using those symbols mu and sigma, or do we have data? And if we have data, then we'll use these symbols y bar and S. It's incorrect to swap those. They mean specific things, and so make sure that you understand that. And if you don't, please ask questions in class, and we can give more examples. All right. There's shorthand notation to describe a normal model, and it's capital N with a parenthesis and then mu and sigma. Okay, so all this, don't let this confuse you. It's just shorthand to say, hey, we've got this normal model here, and the mean is mu, and the standard deviation is sigma. That normal model from the doctor's example with female patients' heights, how could I refer to that normal model? I put N for normal, and then I can find this. Let's see, the mean we used was 64.42 inches, and the standard deviation that we used was about 2.26 inches. That was the smooth curve from the example at the bottom of the previous page. So don't let, this is not confusing. It's just, hey, I've got this normal model with this mean and this standard deviation. All right, so one example just to end this one here. We'll work with IQ scores when we work with normal models quite often just because it's an easy example and most people are pretty familiar with it. IQ scores are normal. The mean is 100 and the standard deviation is 15. Okay. What's the shorthand notation? If I said just, how would you write this model down? This is normal 100, 15, right? Normal model, mean of 100 always comes first. Standard deviation of 15. All right. There's a question at the bottom. We don't need technology to answer this one, but it says here, part B. Draw the correct normal model and shade it to represent the probability that a randomly selected adult has above average IQ. So what's the chance that we just pick somebody off the streets and their IQ is above average or greater than 100? All right, so we'll draw it. If I'm drawing, put the horizontal line first, and then we'll sort of do that. Do your best. We're not going to grade you on your art, but one of my pet peeves is when I see one of these half moons here that is not a normal model. It needs to taper off. So please do not write that one. The mean is 100. We put 100 right in the center. All right. If you were going to label this axis, and we won't do too much labeling here, but one little thing I want to make sure that we do mention. Right about here in the normal model where the curve is cupped downward, and here it turns to cupped upward, this little tick mark here is precisely 115. And how do I know that's 115? Where this changes in the curve from cupped up to cupped down, that's exactly one standard deviation up. So I go 100 plus a 15 is 115. Same thing on the left, right about here. It should be the same distance because this thing's symmetric. So somewhere in here is one standard deviation below the mean. So 100 minus 15, this would be 85. Now that's all the labeling I'll do here because we're going to do a heck of a lot of labeling in the next video. To answer the question, remember that probabilities correspond to probabilities correspond to areas. Draw the correct normal model and shade it. What's the chance or the probability that a randomly selected adult has above average IQ? Here's average. Here's above average. I just straight up there. Easy question. The whole area is 1. That has to be half. This distribution is symmetric, right? This is half. This is half, or 50% chance. Randomly select somebody off the streets. There's a 50% chance they have above average IQ. There's a 50% chance they have below average IQ. All right, so we didn't need technology to answer this question. Pretty easy one, but we do have to start somewhere. All right, so thanks for watching. We will see you in class.